In this video, I will give an overview of the CVPR 2020 UG2 Plus Challenge Track 2 Face Verification on Flatcam Images. I will clarify its basic rules and objective, as well as discuss the data and development kit provided. There are three sub-challenges in this track. The first challenge is on image enhancement. The second is on solving an inverse imaging problem. And the third is on developing a face verification algorithm. I will discuss them in more detail in this video. You are welcome to participate in either one, two, or all three of the sub-challenges. While not all sub-challenges require to design a face verification algorithm, they are all still related to face verification. Generally, a face verification algorithm takes in two images of faces and outputs whether the two images contain the same person or not. This is useful for applications in security, surveillance, social media, and many other domains. Recently, researchers have developed a design for a thin lensless camera called the Flatcam. These cameras can be much thinner and have a much lower cost than standard lens-based cameras. As such, they are beneficial for security systems, Internet of Things sensors, object add-ons, and others. They can be very useful for inference applications, such as face verification in constrained settings. Since it is a lensless camera, it does not immediately capture an image. In fact, its sensor measurements, which we call Flatcam measurements in this challenge, look like this. An algorithm is then required to reconstruct the image out of these sensor measurements. We call the algorithm and its output as Tikhonov reconstruction because it is based on Tikhonov regularized least squares. The measurement model is given by the equation here. Y refers to the 2D Flatcam measurements. X is the 2D scene, and Phi-L and Phi-R are model matrices we obtain through calibration. In the code provided in the development kit, Phi-L is referred to as P1 and Phi-R is referred to as Q1. Tikhonov reconstruction is performed by solving the following regularized least squares problem. The solution is given by the following formula. Here, U sigma V is the singular value decomposition of phi, and lambda is a regularization parameter. This model and the algorithm is described in detail in this paper below by Asif and others. For color images, you would apply this formula to each color channel separately and then merge them together in the end. Let me go into more detail on Tikhonov reconstruction for color images. The Flatcam prototype we use for this challenge contains a Bayer filtered sensor. As such, the sensor measurement is grouped into four types of pixels. The first measures blue wavelengths. The second and the third types measure green wavelengths. The fourth type measures red wavelengths. These four types are then repeated across the sensor. Thus, it is as if we are taking four measurements, each having one color. We obtain calibration matrices for each pixel type separately. As such, in our Tikhonov reconstruction code, you will find P1B and Q1B, P1GB and Q1GB, P1GR and Q1GR, and P1R and Q1R. To perform color reconstruction, we separate out the four pixel types. Perform the Tikhonov reconstruction given by this formula separately on each one, and then put them back together to form an RGB image. For the green channel, we take the average of the two green pixel type reconstructions. This code can be found in the challenge development kit. Here are some sample Tikhonov reconstructions of Flatcam images captured of real human faces. As you can see from the examples, the images produced by Flatcam are quite different from the images produced by a webcam or by standard lens-based cameras. It contains unique types of artifacts, noise, and blurring. As such, current pre-trained face verification algorithms do not work as well with Flatcam images. In this challenge, we aim to change that and to greatly improve the performance of face verification on flat cam images. This will allow us to use the thin and inexpensive flat cam for face verification applications. We explore three different approaches to improve face verification accuracy on flat cam images, giving rise to the three different sub-challenges. For sub-challenge 2.1, your objective is to design an algorithm that takes in a Tikhonov reconstruction and outputs an image that will then be sent to a standard face verification algorithm. Your method may involve denoising, deblurring, and other types of enhancements that can convert these Tikhonov reconstructions into images that are more suitable for currently existing face verification algorithms. Standard face verification algorithms are not trained to handle the unique artifacts of flat cam images. With your image enhancement method, we could immediately use off-the-shelf face verification algorithms without modifying them and still get high performance. As an example, if your method can produce images that resemble lens-based cameras images, then we know that standard face verification algorithms can perform well on them. Note that you will not be designing the face verification algorithm. Instead, on test time, we will use your method to enhance a set of Tikhonov reconstructions. We will then use your method's outputs as inputs to multiple off-the-shelf face verification algorithms. Your objective is to produce outputs that will lead to high performance with off-the-shelf face verification algorithms. Your score will be the average accuracy rates of the face verification algorithms when run on your outputs. These Tikhonov reconstructions have lambda set to 0.0003. Recall that lambda is the regularization parameter from the Tikhonov reconstruction formula. In sub-challenge 2.2, your method should directly receive the flat cam measurement and then output a reconstruction that will yield better performance with off-the-shelf face verification algorithms. Again, you will not design the face verification algorithm. Similar to sub-challenge 2.1, in test time, we will use your method to reconstruct a set of flat cam measurements. We will then use your method's outputs as inputs to multiple standard face verification algorithms. Your objective is to produce outputs that will lead to high performance with these off-the-shelf face verification algorithms. Your score will be the average accuracy rates of the face verification algorithms when run on your outputs. The idea is that perhaps if we do not restrict the first step to be Tikhonov reconstruction, we can get even better performance. Again, as an example, your method may be a function that can map flat cam measurements into images that resemble the images captured by standard lens-based cameras. In sub-challenge 2.3, you will design the full pipeline. Your method will take in a pair of flat cam measurements that pertain to faces and identify whether they are the same person or not. You are free to approach this in multiple ways. For example, you can perform verification on the measurement space. Or perhaps your method will perform some type of reconstruction first and then perform verification on those reconstructions. It is up to you. Your score will be your face verification method's accuracy rate on the pairs of flat cam measurements we will test it with. Next, I discuss the Tikhonov reconstructions and the flat cam measurements we will use to test your algorithms. The flat cam face dataset is a dataset of flat cam measurements and Tikhonov reconstructions of faces captured by a flat cam prototype. The images for 87 subjects are made public. Several other subjects are kept private. These private images are the ones we will test your algorithms on. The conditions the private subjects were captured in are similar to the ones of the public images. Thus, the public flat cam face dataset should give you a good idea of the kinds of test images you can expect. The public flat cam face dataset also contains webcam captures of the subjects, but it is important to note that the correspondence between the webcam images and the flat cam images are not perfect. They both have different perspectives, as the webcam and the flat cam prototype were not in the exact same location, and there may be a time lag between the captures of the two devices. The link to the public flat cam face dataset is also available on the dataset page of the challenge website. Apart from the public flat cam face dataset, we also provide display capture datasets. For these, we point the same FlatCam prototype to a monitor, display images from popular datasets on the monitor, and capture them with the FlatCam. While these are not captures of real faces, these at least come with ground truth images that are better aligned to the FlatCam images. We capture a subset of the Cassia web face dataset and the wider face dataset. These can be found in the dataset page on the challenge website. Your submission must be a Docker image uploaded to Docker Hub. There are multiple tutorials online on converting your application into a Docker image, such as this one. Later in this video, I will show a sample submission and show how it can be converted into a Docker image. As discussed in the guidelines page of the challenge website, we will run a container of your image and mount the test images on it. The guidelines discuss the requirements on your Docker image. For example, for sub-challenge 2.1, we will mount the test Tikhonov reconstructions in a folder called /root/challenge2-1_test_input. Your job is to provide a shell script in /root/UG2_challenge2-1_submission number.sh, where number pertains to the submission number. You may have up to 3 submissions, all in the same Docker image. When we run the shell script, it should take all the images in the test input folder, run your algorithm on each of them, and place them in the folder /root/challenge2-1_test_output/submission number with all the same file names. The procedure for sub-challenge 2.2 is quite similar. For sub-challenge 2.3, wherein you must design a face verification algorithm, we will mount 2 things. The first is a text file /root/challenge2-3_test_pairs.txt. It looks like this. Each line contains the paths to a pair of FlatCam measurements that your method must run verification on. The second thing we will mount is the actual directory of FlatCam measurements that these file names pertain to. Your job is to write a shell script /root/UG2_challenge2-3_submission number.sh that when run must run verification on each pair listed here and output a text file /root/UG2_challenge2-3_test_output_submission number.txt, wherein each line is either a 1 or a 0, referring to whether the corresponding pair of images contains the same person, which is 1, or different people, which is 0. Next, I will discuss the development kit. The link to the development kit can be found in the guidelines page of the challenge website. This is the development kit. This folder contains the Tikhonov reconstruction code. You do not need to use it, but it is here in case you would like to. Reconstruction code is available for both MATLAB and Python. The calibration matrices are stored in flatcam_calibdata.mat. If you open this file in MATLAB, for example, you will see these fields. These P1 and Q1 fields are the calibration matrices I was discussing earlier. I have gone ahead and pre-computed their singular value decompositions for Tikhonov reconstruction. You can go through the code to see exactly how reconstruction is being performed. The MATLAB folder and the Python folder both contain a demo script. These demo scripts perform reconstruction on a single capture. Next, I provide sample submissions for each of the sub-challenges. As I said, the submissions are Docker images that need to be uploaded to Docker Hub. This link contains the sample submissions for each sub-challenge. Note that these sample submissions do not contain any meaningful algorithm. They are just meant to show a sample format for your submissions. In the development kit, I show how I created these Docker images under sample submission. There is a subdirectory for each sub-challenge. Let us look at challenge 2-1, for example. In this example, I have two submissions. My actual algorithms are in these Python scripts. For example, for the first algorithm, I simply copy all the files from the input directory /root/challenge2-1_test_input to the output directory /root/challenge2-1_test_output/submission1. Again, this is just a dummy algorithm for example. Recall from the guidelines that you need to provide a shell script for each submission. Here's my shell script, UG2-1_submission1.sh. In it, I just run my algorithm on Python. I do the same for submission 2. To convert this into a Docker image, I wrote a Docker file. It is very simple. It simply copies all these files into the Docker image and installs the required Python requirements. Running the docker build command then produces the Docker image that I can upload to Docker Hub. You can visit the other examples for the different sub-challenges. I also provide sample evaluation code in the development kit. These do not actually perform the evaluation that will be used in test time. They do not contain the actual test data, and for sub-challenges 2-1 and 2-2, they do not contain the actual face verification algorithms we will run your outputs on. However, you can use it to test the formatting of your submissions. To run the sample evaluation, you'll first need to download sample evaluation data. Follow the instructions in the README. The sample evaluation data is just some images from the public FlatCam face dataset in the appropriate test format. Next, navigating into the sample evaluation directory, we have sample evaluations for each of the sub-challenges. Let us look again at sub-challenge 2-1. To test your submission, open evaluate_challenge2-1.sh and change the Docker image to your submission. As you can see, the evaluation script will run your Docker container and mount the test images into the folder /root/challenge2-1_test_input. Then it will run this run submissions.sh shell script that will basically run all your submissions. Afterwards, it will run a separate Docker container that we have prepared for the actual evaluation.
If it all works out, if you open the outputs folder in the corresponding evaluation folder, you will see a verification_scores.txt file containing the scores for each of your submission. Again, this sample evaluation does not actually perform a real verification algorithm, so ignore the actual scores given. However, you could check that the evaluation code successfully completes running without any errors to see if you have formatted your submission correctly.
That is it for this video. For any questions, concerns, or comments, please email us at cvpr2020.ug2challenge.track2@gmail.com. We will be happy to answer any questions and assist you throughout this challenge. We hope you enjoyed this unique challenge that bridges the latest in computational photography and visual recognition.